Good afternoon and welcome to this introduction to large language models. The idea behind this presentation is that there are many LLM-based tools available and they are very easy to use. So this isn't a traditional training where we try to understand how things work, and I'm not the right person for that anyway. Instead, we are facing a flood of potential tools and as an institute, we're still figuring out the best way to adopt them. I'm part of the QAB Research Integrity Committee, for example, and these tools evolve faster than we can have a discussion about them. But they are interesting and accessible to anyone. This isn't training just for researchers. Any member of staff at our institute can access these tools and they can be useful across different roles. That's why I've prepared a short introduction to demystify what these tools are and to start a conversation. I'm really looking forward to hearing from you as well, so at some point we will pause the presentation and I will ask you two questions. What tools are making your work better? And second, what tasks can you achieve with ChatGPT or similar tools? And what would you like to do that you haven't been able to achieve at a satisfactory level yet? Now, to show that this isn't purely technical, I will start with an anecdote. My interest in the technology behind ChatGPT started a long time ago. During my PhD, I became interested in an American show called Jeopardy that I'd never heard before. So if you, like me, don't know what it is, it's like a reverse pub quiz where the host gives you the answer and you have to come up with the question. So the reason why I got interested was that IBM sent a supercomputer called Watson to compete on the show, and this is how it played.
Even a broken one of these on your wall is right twice a day. Watson.
What is clock?
Clock is correct, and with that you move.
And so this was a computer playing Jeopardy. Spoiler alert, Watson won. What is interesting is that at some point you saw an overlay graphics where there were three possible answers and they were ranked by confidence, like some were more likely than the other. And it's interesting to see how wrong the others were. So there was clearly no reasoning. There was a probabilistic model that allowed Watson to get the answer. The computer was a massive supercomputer offline that was playing the game, and it was impressive by the time. But this was a long time ago. So let's try to see what are the basic steps in simple words that it took to get to ChatGPT. Let's start with a step back. I think you're all familiar with a plot like this. You collect some data and you plot it on an XY graph. In this case, and this comes from a Google training, like all the links are in the presentation and on the website, so you can go further later. We're looking at the weight of engines, and I apologize for the imperial units. This is from an American source, right? On the y-axis, we have the efficiency in miles per gallon. Now you plot the data and this is what you see. This is what you do in every lab every day. When we move into the, let's say, machine learning space, we are interested in making predictions. So here we highlight two different terms, feature and label. Here's what they mean. We have data points, but we're interested in making predictions in the future. So what it is to measure from an engine is its weight. That's our feature. What we want to predict is the efficiency, and that's our label. We can do some basic linear regression, and this blue line is a model that we can use to make predictions. Now, borrowing again some jargon from linear regression, we have two parameters, B and W1 in this case, and one is called bias and the other weight. Together, they define which linear line of all the possible ones fits our data. So the training of the model is finding the two parameters that are the best to fit the data that we observed. Now, a more complicated way to make prediction is when we don't really know the exact nature of the relationship between our data. The linear regression works if our data is linearly correlated, right? But when the relationship is more complex, we can use neural networks to model information that we don't fully understand. This is a classic dataset. Again, we have features. Someone collected a lot of data, measurements about iris flowers. They measure the sepal length, the sepal width, the petal length, and the petal width. So we have 4 features. Now, there are 3 different species of iris. Botanists, of course, can classify them just looking at a photo of the flower. The question is, can these 4 measurements be used to predict the species? So first, is there enough separation of these features in real life to make the distinction? I can tell you, yes, someone did an exploratory data analysis and confirmed it. But now we want to build a machine that can predict, if you want, an algorithm that can take these 4 numbers and tell us the classification. And one approach is to use a neural network. What you see in the figure here is a typical diagram. You put 4 features in the input layer, because we have 4 measures. Then each gray node is a simple mathematical function. They are simple individually, but they have some parameters that of course will change the output of the function. So we have a set of parameters, as many as the neurons of the network. And because you combine many of them together, complex patterns can start to emerge. Now, of course, we also specify the number of output layer. In this case, we have 3 species, so we design the network to have 3 outputs, and the network will give us 3 values, and we assume that the highest is our classification. So the first neuron will be for setosa, the second for versicolored, and the third for virginica. How does this work? Every node, every gray dot that you see has parameters, like the weight and the bias that we saw before, and it's just a matter of finding the right parameters to make this network useful. So there's a training step where we keep feeding inputs from our dataset, and the computer tunes the parameters to get better results. Now, as you can see, this network has 2 layers, so it's different from the one before. The point is, we can engineer the network to have whatever shape we want, and of course the more nodes means more parameters, so it will take longer to train it. And the training step is this. We use known answers to train the network, and then we want to actually use it. So the real goal is to have a model that allows us to classify new flowers that we photograph or we take measures from in our garden. To put it simply, all the parameters that in the network can store information. Ideally, these store smart information, so the way to convert an input to an output. But if you have a lot of parameters that you can train, they can act like a memory in a big brain. So, as we say about students, some can be smart and figure out how to do things, others less smart and memorize everything. So, the risk of training neural networks is that they might memorize the training set, and this is called overfitting. So, it's not really good at classifying new things, it's just memorize the data set. The typical approach in practice, so, is to split our known data into 2 buckets. We use the first bucket to train the network, and the second bucket to test the network. So the first is the training set, and the second is the test set. Again, I think this just helps to demystify the fact that we can do something quite complicated with some mathematical functions. So this network has as input for length. Someone measured for length in a flower, but as you can imagine, we can use neural networks to classify and work on different kind of inputs, like photos, images. So another very famous data set is a set of handwritten digits that were scanned. So the goal is to take one image with one digit, and the machine should be able to read the digit in the image. This was a challenge for postal services, trying to automatically scan zip codes from postcards, for example. So we have a large data sets with a lot of digits, and they are all already classified, so we know which are the ones, which are the twos, and so on and forth. So the question is, can we use this set as a training set for a neural network that can classify new digits in the future? The key point here is we can turn our input, that is an image, into numbers, and that's what we need to do. So neural networks ingest numbers, and in this case each image is scaled to a specific size, 28 by 28 pixels, and in total this means we have 784 values. So each pixel here is in grayscale. So It's a value from 0 to 255, for example, the intensity of the gray. Now, as you can see, you lose the two-dimensional shape of the image here. Each input neuron is just holding a specific pixel value. There's nothing that tells us in the network this pixel is next to this pixel. This network doesn't see the spatial structure, it just sees the input as 784 numbers. But we can still train the network, and if we are successful in the end, we'll have a machine that can classify our figure into one of the possible digits, 0 through 9. Is this clear? Something that may seem obvious, but I should clarify. If I write the letter A there as an input, the output will still be one of the neurons from 0 to 9, because this is how the network is engineered and trained. Maybe with a lower confidence, maybe there will be ambiguities, but the output can only be a digit from 0 to 9. If there's a digit that looks like an A, that will be the one that gets classified. And if we click on the slide, we can go to a website where we can play with this in real time and see how the network works. So this is the real algorithm working in a web browser. I think it's quite impressive. So the way because this is just functions that will process numbers, the network has 9 possible outputs, and in this case quite obvious that Z and 2 are similar, but if you do something completely different, you will still get one of those answers. You would need a different network that has the ability. Usually you can classify letter or digit or letter, this kind of thing. You can do something that is a pre-filter, but if those are your options, that's what you can get. So it's a good point. As you can see, this is a good 5, depending, because in the training set, this kind of shape, in the training set, the number 5 was triggering the functions in a way that somehow, that we cannot understand, get the same result from that. Yes, exactly. We get exactly to that. But it's a very good point. And I think in general, the point is that we should understand what the tool can do. So back to language processing. The example I showed you so far are doing the typical thing that machine learning can do. And this is a super easy book about machine learning. It's in the website, I will tell you later, but it's all illustrated. It's the nice evening reading. The traditional machine learning can be separated into 2 different approaches. One is to predict values, and the other is to classify things into boxes. The 2 typical things that you can do. And the engine example is the first class, the iris or the digit classification the second type of thing. Now let's shift gears completely and talk about language, about how machines can work with text. On your phone's keyboard, for example, you have this prediction of the next word. This uses a very simple algorithm called the n-gram. Here's how it works. You have a training set, maybe your messages, Wikipedia, whatever. You chop it into fragments of n words, let's say 3 words, and then, based on the first n-1 words, you keep track of the frequencies of what the last word could be. That gives you a prediction, or better, a set of predictions. This has been in our pockets for years, and it never made us go, wow, because it's very simple to understand what's happening. So we're not surprised when we get wrong suggestions, and when we get a good suggestion, we just tap on it and we don't think something magical happened. It's just basic statistics that we can understand. But here's the limitation. Because we chop the text in smaller pieces, we don't have context. We don't have meaning. It's just next word prediction based on the few words that come first. So how did we move from this to ChatGPT? And I'm still amazed that this happened. Again, I'm probably not the right person to tell you about the details, but the point is we are trained just to give an overview, to understand the limitations and how based on training we can get models. So remember, when I said to you that you can make a neural network whatever size you want, Well, for a long time, there was this feeling that a big neural network were probably not a good idea. Partly because they are computationally expensive, but also because there was this thinking. You're basically encouraging the network to memorize the entire data sets within the parameters, because there are so many parameters. So for a long time, the ingenuity in neural network was trying to make smart networks and not big networks. LLMs proved this wrong. And there's also some research showing that it's true that to a certain point you decrease your ability to make predictions, but then keeping growing, the network then starts learning again. Among the limitations of this approach is that the context is limited and we have to process the text one bit at a time. The breakthrough discovery happened in 2017 when a group of engineers at Google came up with a new kind of network called the transformer. The key innovation of the transformer is that it allows massive parallelism. And so while traditional neural networks has to process information sequentially, one step at a time, the transformer architecture can process many data parts simultaneously, which makes it much faster to train on huge amount of data. And this is what made it possible to scale up to massive networks that we see today. The transformer architecture is the foundation behind large language models like ChatGPT. As we said before, to process data that is not numbers, we need to first convert it to numbers. So there's a process called tokenization, where we break sentences into smaller pieces called tokens, and each token is represented by a vector, so a list of numbers, and it's called an embedding. The vector captures the meaning so that similar words have similar vectors. The embedding process is fascinating. Each tokens become a vector that captures context and meaning, and this is done by training. And the vector space has as many dimensions as the values in the vector. And a famous example is if you take the vector for king and subtract the vector for man, then you get a very close vector to the one that embeds queen. So the relationship between words are encoded in vectors. And this embedding is learned through machine learning, trained on massive amounts of text. Now, the attention layer is where the magic happens. It's a set of functions that adjust the values on each token based on the tokens around it, before and after. So this was crucial to the emergence of ChatGPT. With this mechanism, we are soaking every token with the context of the surrounding tokens, and as you can see from the animation, this process is highly parallelized, so we can take the entire text and process it. So the second breakthrough that allows this parallelization is allowed by new architectures where you can process all the tokens simultaneously rather than sequentially. Then there is another layer called feed-forward layers that further process the information. As you can see, in this case, each token is adjusted but not based on the tokens next to it. And we have a lot of attention and feed-forward layers until at the end, the last token has captured all the context of the entire sentence. And at that point, we have a very sophisticated next word prediction to generate the most likely next token. So now you know what's the transformer, and GPT stands for Generative Pre-trained Transformer. This is the engine of ChatGPT.
But the focus of today's chat is not the engine, it's the tool. Because to use the tool, we just need a keyboard and a browser. We don't need to know that there are vectors behind it. But I think it's quite useful to understand that in the simplest terms, ChatGPT is able to predict the next word given a text. So how could OpenAI make a product that is actually useful and not just a keyboard that allows us to type messages faster?
There is a trick. When we type something into ChatGPT, the model doesn't just receive our text, it receives a much bigger text. This is the trick that transforms the transformer into a chatbot. The bigger text includes instructions like, you are a helpful assistant, the user is asking you this question, and so on and forth. So basically, you are priming the network to respond as an assistant. Then, when the network generates a token, that is added to the input again, and the prediction starts again, so that you can add another token and another token until you generate an end of sentence token that was learned during the training. So one consequence of this is that when ChatGPT starts answering to us, it doesn't know where it's going to end. It's generating token by token, building the response as it goes, and it feels like magic.
How can we feel the, let's say, the fingerprint of the training of the massive amount of text that these language models were trained on in real life? So this is an experiment done with an old version of ChatGPT, and it's a question that we can read. 4 people need to cross a rickety bridge at night. The 4 people walk at different speeds. One can cross the bridge in 1 minute, another one in 2 minutes, the third one in 5 minutes, and the slowest in 10 minutes. When multiple people cross the bridge together, they must go at the slower person pace. The speed of people crossing the bridge together is limited by the slower person. So, I assume the question is, how long does it take to cross the bridge? What's your take? Okay, so the natural intelligence is telling 10 minutes. Let's check what the artificial intelligence was answering to this riddle. Certainly, let's go through the solution of this puzzle. The 2 fastest people, A and B, cross the bridge in 2 minutes. A goes back with a flashlight, taking 1 minute. What flashlight? The 2 slowest people, C and so on forth. So the answer is 17 minutes. And these, I think, captures 90% of what I wanted to tell you today. That is, ChatGPT is very good at giving answers that sounds credible and sophisticated because they are. They are credible, it's good English, they are well structured, and they are sophisticated. But this does not guarantee that they are correct. But we can try to understand what happened there. So as I said, ChatGPT has been trained on a massive amount of text, basically everything that was possible to ingest. And this includes a lot of real quizzes. For example, there are books of HR interviews manuals, and a typical question is this one. So the person testing ChatGPT took the typical question and removed one key part, but this tricked ChatGPT into answering the wrong answer, basically. This was done several years ago, so I was wondering, is this still a thing? And someone made a similar experiment recently. A dead cat is placed into a box along a nuclear isotope, a viral poison, and a radiation detector. What's the probability of the cat being alive? So if the cat is dead, the probability is 0. But this sounds, except the first adjective, this sounds very similar to the Schrödinger paradox. So you get the right answer to the wrong question, in a way. So we're still there. We have a powerful tool that I'm impressed every day I use it. But we need to understand that it's good at something that is, for example, for creating text, but it's not really good at giving you the right answer to questions. And I tried this morning with DeepSeek, and without the thinking mode, I got the same error. With the thinking mode, the dead part of the question was captured. So it's still a thing, implications. So the first to me, it's difficult not to have AI around you, either because this one feed from The Economist 2 weeks ago, 1 week ago, 1 month ago, 1 week ago, 3 weeks ago, it was AI every day. And then we all use Microsoft Office, and now they are putting Copilot everywhere. I try to, usually when I wanted to go to the web version, it was office.com. Now if you go to Office, you get Copilot. So I don't know where my documents are anymore. I don't think it's a big loss. And this is paired to another phenomenon that's quite interesting. So in general, there's a theorem that, when you get, this was forged before ChatGPT. It was in the no-vax debate. The time you spend debunking wrong information is magnitudes, order of magnitudes higher than the time to just bullshit people. Now we have a machine that can, generate a high amount of and what I like is that a tool that was decent in the past, Grammarly, now has AI, and the native speaker will tell me what is this what's going on there? I disabled Grammarly on most of my websites because I cannot trust that anymore. To me, this is a problem. So the fact that it takes higher amount of time to debunk things than it is to produce them, it's still something that I'm not ready to address myself. I was chatting with the Institute statistician about code generated with ChatGPT, and I generate code every day with all the possible tools. And we're discussing about the fact that he asked for an R function that was calculating some diversity metrics, and this is for you. The function was generated, and it was syntactically correct. So it was running in R, but was just giving the wrong numbers.
Sometimes it does that. And in that case, you have to be careful about what
So the consequence is that for me, writing code is boring, but reading code is massively more boring. So checking the code that ChatGPT does, it's terrible because it has a style that is not mine, and it's not fun in any case to read code. So I'm still a bit debated. For example, sometimes I do the opposite of you. I write the test myself, and then I ask ChatGPT to pass the test. But yes, I understand that, I think it's good to have a kind of balanced approach so that we have a corner in our workflow where we have the control. But someone said it's better than Google to find information. The problem is that as Copilot is everywhere, also AI is everywhere. So Google basically turned on automatic summaries, and this is what you get when you have LLMs answering your questions on Google. If you look for screenshots, there are plenty of examples. And it's very interesting that the order of the words will just change the summary to the opposite. So, and again, this is just similar to the HR test. Basically, you can trigger assumption based on what the training was. The second is, the internet is full of, let's say, satirical sites or people making fun things on Reddit, and that's training set. So some answers are actually based. If you try to understand why this happens, usually it is because there is a lot of information that is just not factually correct, and it's trained on.
A lot of the LLMs seem to accept the premise of the question.
Yes.
They don't turn around and go, that's a stupid question, because it's not trained to do that.
Yes. And this is also a problem, because initially when these tools came out, people would say, oh, but what about reproducibility? And I was saying to myself, it's not really important to get word by word the same answer. Reproducible is not exactly that. It's very easy to check if something is word by word the same. And one of the use that we all do is getting summaries. Someone did a preprint comparing some models. Again, this is quite old. But the point is, we read the summary and we are happy. Few of us, but not everyone and not every day, we don't read also the original paper because that's not the point of getting a summary out of it. But if you don't compare, you don't know exactly if the summary is correct or looks correct because it's usually really good looking. So in terms of factuality, comprehensiveness, you see there is a trade-off. So usually if you are correct, you may be not comprehensive, you are omitting some information. So in general, these tools are, in my opinion, really good. But again, you might trigger the case where your input text resembles to something, and then you might get something not necessarily correct out of it. I do believe that we are responsible for the use that we do. And this is a slide from a presentation of the last century, 1979. A computer can never be held accountable. Therefore, a computer must never make a management decision or any decision. And to me, this is still valid. So we should be informed enough about these tools and then make decisions and decide when to use them. Again, this is a figure of a paper published a year ago that for some reason sparked criticism. But the trend was not off because this is very recent from a review or a paper in Scientific Reports, I think. And again, it's massively disrespectful to publish papers with these images because you didn't use GPT to generate the image. You didn't use your eyes to check what you generated. That's the basic of accountability. You generate an image and then you have to at least evaluate it. Then there are paragraphs like, as of my last knowledge update. Or certainly, here is a possible introduction for your topic. Again, this is not bad because you use GPT, it's bad because you didn't read the output. Otherwise, you would have just deleted that sentence. Now, deleting the sentence is not making things correct, because of course, you don't know if what was generated was correct.
Thank you for watching this introduction to the course. During the class, we will learn how to use ChatGPT and other tools like Claude and Perplexity. We will explore prompt engineering techniques to write more effective prompts. We will see how some tools like Elicit or SciSpace are using LLMs to specifically support scientific literature tasks like reviews and data exchange. We will see examples of using ChatGPT for exploratory data analysis, in which case, using dedicated GPT, our prompt can include data, in this case, comma-separated values, and the output will not be generated from the model, but the model will generate some code to then generate plots. So if this is the case, then the plots will reflect our data, will not be hallucinations, but of course we must check that the code produced to make the plots is actually correct. Finally, we will cover privacy settings and how to opt out of model training. We will explore how to use AI agents for code generation and leveraging local AI to maintain control over confidential information. I look forward to meeting you and discussing AI tools and responsible use together.